Okay, so before we talk about the histology of bone, I want to remind you where compact bone and spongy bone will be located. So remember, compact bone, we're looking at a long bone here. Compact bone is located around the periphery, right? Whereas spongy bone is located in the middle of the epiphyses. This is all spongy bone. Now in the medullary cavity, there's a thin layer of spongy bone that's on the inside, but most of it has been carved out to form that medullary cavity. Now in short, flat, irregular, and sesamoid bones, we see the little compact bone, spongy bone sandwich, right? Compact bone around the periphery again, and then spongy bone sandwiched in between the two compact bone layers. So I just want you to keep that in mind when we talk about the histology of bone, all right? And the overall, how the structure of compact bone and spongy bone differ based on the functions, the specific functions they have to carry out. All right, so compact bone, it's called compact because it's very densely compacted. The extracellular matrix is very densely compacted into these structural units called osteons, okay? So if we look, this would be like a cross section through the diaphysis of a long bone. Here's our compact bone around the periphery, and here's that thin layer of spongy bone. This cavity right here would be the medullary cavity. And if we look at the compact bone, we can see these this is a unit, this is a unit, this is a unit. These functional units are called osteons. Think of it as like a densely, so the book gives you an example of compact bone looks like a forest of tightly packed trees. Each one of these quote unquote trees would be an osteon, or you can call it a Haversian system. I like just calling it an osteon, but these are the functional units of the compact bone. Now notice that each osteon have concentric circles, right? Here's a concentric circle, another one. These concentric circles are the extracellular matrix that is laid down and formed by the osteocytes, which are these little like spider-looking cells that are sandwiched in between the concentric circles. These concentric circles are called lamellae. And lamellae are just concentric rings of bone matrix, okay? That has been laid down by those osteocytes, by the osteoblasts that eventually became osteocytes. Okay, so each osteon will contain between like 4 and 20 lamellae, depending on what bone we're talking about, where it's located. Again, concentric circles of the bone matrix. And that lamellar arrangement is very stress resistant. So if we were to think, okay, let's go back to here. These osteons run the length of the long bone, okay? So if we go back to our picture of a long bone, the osteons would run the length of the bone, right? And just like tree trunks, right? If you were to see a cross section through a tree, you would see concentric circles of tree that has been laid down. And all of that, it runs the length of the tree trunk, and it helps resist compression, and it acts as a weight-bearing pillar. So that's what these osteons do for compact bone. Osteons act as weight-bearing pillars. All right. So again, these osteons run the length of the long bone, and they act as weight-bearing pillars, just like tree trunks do for trees. Or if we're talking about beams within a building, columns on your front porch, what do they all do? They are weight-bearing pillars. Osteons do the same thing. Okay. These concentric circles of lamellae that create this osteon, they act as weight-bearing pillars, okay? And they're very resistant to stress, okay? Then through the collagen fibers will actually run in opposite directions to the osteons, and that is to allow resisting of twisting and bending forces. Right? So whatever orientation those osteons are running, those lamellae are running within the osteon, The collagen fibers of the organic matrix will be running in opposite directions. Okay, so within an osteon, let's talk about some structures that we see. Now, this internal canal, right, is called a central canal. It's lined with endosteum. And then what we see contained within the central canal are blood vessels and a nerve supply. Remember, bone is very well vascularized. If you get a break in a bone, that will heal faster than, say, a break in your cartilage. And that's because bone is very well vascularized. Every osteon, every unit has a central canal that contains arteries, veins, and nerves, okay? Now, how do we get the lacunae, right? Or how do we get the lamellae? The lamellae are the concentric circles of bone matrix that gets laid down by osteoblasts. And eventually, remember, those osteoblasts surround themselves, like right here, they surround themselves with the bone matrix, and they enclose themselves in a lacunae, and they become osteocytes. So all these guys are osteocytes. And remember this picture from the last video, osteocytes have these really long cytoplasmic extensions. The blue space around these osteocytes, that represents the lacunae, which is their little quote-unquote home, all right? It's the cavity that these cells exist in. And the cytoplasmic processes connect osteocyte to osteocyte. And then you'll also see cytoplasmic processes eventually reaching the central canal. All right, so these little canals, these little channels that allow these cytoplasmic processes of neighboring osteocytes to connect, these are called canaliculi. So canaliculi are these channels that allow osteocytes to connect their cytoplasmic processes, right? So canaliculi, canal, iculi refers to, it's like little, so little canals, all right? Now the cytoplasmic processes of these neighboring osteocytes will be connected via gap junctions. And when you think gap junctions, remember sharing cytoplasm. It allows molecules, substances, it essentially allows sharing of cytoplasm, and for molecules to be passed from one osteocyte to another. So these canaliculi, these little channels, not only connect osteocyte to neighboring osteocytes, they also eventually connect the osteocytes within this osteon to the central canal. This allows for nutrients to go from the blood vessels of the central canal to all of the osteocytes within this osteon, and waste products from all these osteocytes to go back to the blood for them to get rid of the waste products into the venule that's located here, okay? All right, so what do these canaliculi do? They allow for communication between osteocytes as well as diffusion of nutrients and waste between the osteocytes and the central canal. Now looking at, so if you see these functional units, these osteons, right? Tree trunk, tree trunk, tree trunk. You'll notice that there are some lamellae that aren't really, they're kind of in between the osteons, but they don't form circles. These are what's called interstitial lamellae, and they are remnants of old osteons. Remember, bone is dynamic. It's constantly being remodeled. It's being broken down and new bone is formed. So these interstitial lamellae that are kind of sandwiched in between osteons but don't make complete circles, those are interstitial lamellae, and they're remnants of old osteons. All right? Remember, osteons are not permanent structures. Remember, bone is dynamic, constantly being remodeled. So let's talk about what perforating canals or Volkmann's canals, you can call them either or. It's called perforating because, I like this picture. Here, this would be the periosteum. Remember, what's one of the functions of the periosteum? It provides the vasculature and the nervous supply to the bone. So here are all those nutrient arteries, and there's, all these blood vessels and nerves that are embedded in the periosteum is supplying those blood vessels and nerves to the bone, but they have to get into the bone, right? So if you look, the perforating or Volkmann's canals are holes within the bone that run perpendicular to the length of the osteons. So here the osteons running the length of the bone, perforating canals run perpendicular. And the purpose of these perforating canals is to allow blood vessels and nerves to penetrate through the bone from the periosteum inward all the way to the endosteum, which would be lining this medullary cavity, okay? And look, so blood vessels go through these perforating canals and then branch off into this central canal. And then they branch through this perforating canal and then branch into this central canal. So they allow for the innervation of blood vessels and nerves, okay, throughout the bone. That's what perforating or Volkmann's canals are, okay? Here, this is a histology slide of compact bone. This would be an osteon. This dark circle right here in the center, this would be our central canal. This is where we would see the nutrient supply as well as the nervous tissue supply for this osteon. These are concentric circles, which are the lamellae, which is the bone matrix, made up of both the inorganic and organic matrix. These little guys, these are all the osteocytes. And if you look, these little extensions that are running perpendicular, so the concentric circles are going this way, but there are these little lines that are coming off perpendicular to the lamellae, right off of the osteocytes. Those little extensions coming off this way, those are all the canaliculi. Okay, remember canaliculi are those little channels that allow for communication between osteocytes as well as between osteocytes and the central canal. Okay. So now spongy bone, the structure of spongy bone. Now spongy bone is located in the center of the epiphyses or sandwiched in between the compact bone if we're talking about the flat, short, irregular sesamoid bones, okay? Spongy bone, because of its structure, its porous, spongy-like structure, it's not very good for bearing weight. That's why we see it sandwiched in the middle. We don't see it around the outside. Compact bone is really good at bearing weight because of those osteons, those weight-bearing pillars. Now, the fact that this bone is oriented in all different directions does allow it to be able to resist forces from a variety of directions, right? It also, spongy bone, so it will help resist forces in a variety of directions, but most of the compressive twisting forces and stretching forces that a bone will experience that protection will come from the compact bone. Spongy bone also, because of its porous, spongy nature, helps reduce the weight of the overall bone. Again, if it were just compact bone all the way through, we would be super heavy because of it. And then these cavities, these pores that are created by the spongy structure is going to be filled with red bone marrow. So the spongy bone also houses and provides protection to the very important red bone marrow, which produces all of our blood cells. Now, if we look at the histological structure of spongy bone, it's similar in that we see, okay, here are osteocytes. Those osteocytes are embedded in concentric lamellae, right? These concentric lamellae are going to be that bone matrix, both inorganic and organic matrix that's laid down by the younger osteoblast. These osteocytes have canaliculi that are going to allow for communication between neighboring osteocytes. But we do not see an osteon the way we saw it here. The way we saw it here. There's no central canal. And then there's also no perforating canals. So how do the osteocytes get nutrients, right? If there's no central canal that contains blood vessels and there's no perforating canals that allow blood vessels to come in. These osteocytes of spongy bone are primarily going to get their nutrients from the blood vessels that are found in the red bone marrow. So remember, red bone marrow is found in the cavities of spongy bone. Let's go back to, all the way back to this slide. Right. Here's our spongy bone. All that red tissue that's enclosed in the spongy bone and protected by the spongy bone, that's all red bone marrow. Red bone marrow is very well vascularized. So the osteocytes of spongy bone will get their nutrients from the red bone, the vasculature of the red bone marrow. That's going to be all around, housed in the cavities that are provided by the spongy bone. And then this, if you want to read this, this is just using what you've learned to understand a disease state. This is osteopetrosis, not osteoporosis. That's discussed later on in the chapter. But if you want to read through this, again, it won't be on the exam per se, but it's interesting. And if you're in healthcare, you might want to put what you've learned to a clinical use as far as a disease state of bone. Okay?